MCA Prep Packet, Day 4. We're working on reviewing Chapter 3 today, so we're starting on page 15 in your packet. Our first benchmark is 8213. Understand that a function is linear if it can be expressed in the form f of x equals mx plus b, or if its graph is a straight line. Number 1, part A. What term best describes the graph of f of x equals mx? What term describes it? That would be linear. F of x equals mx is the same as f of x equals mx plus 0, so the y-intercept is 0 in this equation. Draw a possible graph of f of x equals mx. That would be any line that goes through the origin. Any line that goes through the origin. So the origin is right here. My y-intercept is 0. Here's a line with a negative slope that goes through the origin. Here's a line with a positive slope that goes through the origin. Here's another line with a positive slope that goes through the origin. All of those lines go through the origin, 0, 0, so they all have a y-intercept of 0. Their equations could all be written in that form, f of x equals mx. Not only are they linear, but another vocab word that we worked on said that they are proportional. So linear is when your graph is a line. Linear and proportional is when it's a line that goes through the origin. So those lines that I drew, and the x and y axis actually, they're all lines that go through 0, 0. They're linear and proportional. The next page that we're on is page 17, 8214. Understand that an arithmetic sequence is a linear function that can be expressed in the form f of x equals mx plus b, where x equals 0, 1, 2, 3, and so on. Part number 1, part A. Write an equation in the form f of x equals mx plus b for the arithmetic sequence 3, 7, 11, 15, 19, 23, and so on, for x equals 0, 1, 2, 3, and so on. Arithmetic sequences are sequences that have addition or subtraction patterns, where the same thing is being added or subtracted over and over. So adding or subtracting patterns where you've got a common difference being added or subtracted over and over. In your equation, f of x equals mx plus b, m represents the common difference. So that number that's being added every time or subtracted every time goes in front of the variable x. Then b, we think of as like the y-intercept when you're graphing. That's your starting point, so it's the first term in the sequence. And that term represents when x equals 0 in your equation. So this sequence is going up 4 each time. So my common difference is 4. So f of x equals 4x. And then plus, the first term is 3, so plus 3. That would be my solution. F of x equals 4x plus 3. That equation represents the sequence of numbers for x equals 0, 1, 2, 3, and so on. Now, what is the 51st term? The 51st term. Well, when x equals 0, look at what happens. F of 0 equals 0 plus 3, which is 3. So when x equals 0, I get the first term in my sequence. So think about this. X equals 0, I get my first term. So then if x equals 1, I will get my second term. If x equals 2, I get my third term. So what am I going to do to get my 51st term? 51st term. What does x equal? Do you see the pattern here? First term x is 0. Second x is 1. Third x is 2. So 51st x is going to be equal to 50. So I am going to plug in 50. So f of 50 equals 4 times 50 plus 3. 4 times 50 is 200 plus 3, 203. So the 51st term, because I do not want to keep writing these numbers out until I get to the 51st term in the sequence. That's going to take me forever. It's much quicker to use that rule. The danger, though, of course, is thinking that the 51st term you're going to plug in 51. And that isn't going to work with the way that this benchmark is written, because it says where x equals 0, 1, 2, 3, and so on, not where x equals 1, 2, 3. So be careful. My next benchmark on the next page, 8215, so this should be on page 21, or page 19, sorry. Understand that a geometric sequence is a nonlinear function, so it's not a straight line. And it can be expressed in the form f of x equals ab to the power of x, where x equals 0, 1, 2, 3, and so on. So nonlinear, geometric sequences, have patterns that involve the same number being multiplied or divided over and over. So multiplication, division patterns, not adding, subtracting anymore. And these are a little bit tricky to work with. When you have the same number being multiplied or divided over and over, we think about the term common ratio, and when you're using this formula or this equation, A represents the first term, and then B represents the common ratio. So what is being multiplied by each time? What it's being multiplied by each time. Notice that this equation is written as multiplication only. So you've got to be able to think about division as a multiplication relationship instead. So for example, dividing by 2 is the same as multiplying by 1/2. Dividing by 3 is the same as multiplying by 1/3. So you've got to be able to express your ratios as multiplication every time. So this sequence that we're working with here, it's multiplied by 3 every time. And the first term is 2. So my rule would be first term first, and then multiplied by 3 every time with the power of x. You may also see this written with parentheses, especially if it was multiplied by a negative number. So either way, you could write that general form. Now, what is the 9th term in the sequence? Just like I explained on the previous example, when x equals 0, you get your first term. So x equals 0 gives you the first term. X equals 1 gives you the second term. So if I'm looking for the 9th term, I am going to have to put in 8 for x. So f of 8 equals 2 times 3 to the 8th power. Of course, the calculator is going to come in handy on this problem. So 2 times 3 to the power of 8 equals 13,122. Again, if you don't think you're going to remember that there's a difference between what you're plugging in, that you're not plugging in 9 to get the 9th term, on this one it would be a lot more reasonable to just keep on multiplying in that sequence. I mean, they give you the first 5 terms, so you could certainly just keep multiplying by 3 each time until you get to the 9th term. That's not unreasonable. Okay, our last benchmark for today, 8221. Represent linear functions with tables, verbal descriptions, symbols, equations, and graphs. Translate one representation to another. Part A, use the table to find the equation for the linear function. Okay, so we have a table. I am going to draw a graph to go with this table. -2, -10. -1, -6. 0, -2, and 1, 2. So this is a linear relationship. The slope and intercept are what I would need in order to write my equation. The slope and intercept. So the slope of this line, I'm going to rise 1, 2, 3, 4, and then run 1. Rise 4, run 1. So my slope is 4. And my y-intercept is -2. So this would be the equation for my line. From the table, you could get this information. I just think it's easier from the graph. From the table, you can tell that y is going up 4 and x is going up 1 each time. So that slope is the change in y divided by the change in x. 4 divided by 1 equals 4. Rate of change and slope are the same thing. Change in y over change in x. And then the intercept, you would be able to see right here, when x equals 0, y is -2. Now, to write a verbal description of the function, you've got a lot of different things that you could say about this. So I am just going to say, this is a linear equation, or a linear function. I'll use their function word. So this is a linear function with the slope of 4. And a y-intercept of -2. Okay, that's it for day 4. So you should be able to finish all of those pages in the packet related to chapter 3.